All right, welcome to The Explainer. Today we're going to pull back the curtain on a core concept in finance and data science, the discrete random variable. Now I know it might sound a little intimidating, but trust me, it's the tool that professionals use to take the guesswork out of really big decisions, to turn that vague feeling of uncertainty into hard numbers you can actually act on.
So look, instead of starting with some dry textbook definition, let's jump right into a real-world problem. Imagine you're a portfolio manager. You're staring at a whole pool of potential investments, and it's your job to make the smartest move. But here's the real question, right? How do you quantify the risk before you commit any capital?
Okay, so this is going to be our puzzle for today. We've got 6 assets in total. 4 of them are high risk, 2 are low risk, and you have to pick 3 at random. The core question is, what are the actual numerical odds of picking a portfolio that's heavy on the high-risk side? This is exactly the kind of uncertainty professionals face every single day.
To solve this, we can't just talk about good or bad outcomes. That's too vague. We need a way to translate chance into numbers we can actually work with. And for that, we need our first essential tool, the random variable.
So what is a random variable? Honestly, it's just a rule. That's it. Think of it as a translator. It takes every possible result of some random event, like picking assets or flipping a coin, and it just assigns a number to it. It's what turns real-world outcomes into a mathematical language we can use. And for our purposes today, we're just going to call it Y.
Let's look at a super simple example to see how this works. If we toss 2 coins, our experiment has 4 possible outcomes, right? Our random variable y is defined as the number of heads. So if we get 2 heads, y equals 2. If we get 1 head and 1 tail, y equals 1. No heads? Well, y is 0. And just like that, we've translated the physical outcomes into a simple, clean set of numbers, 2, 1, and 0.
Okay, so we have our translator. We can turn outcomes into numbers. But that's only half the story. A number isn't all that useful unless we know how likely it is to actually pop up. And for that, we need a blueprint.
This blueprint is called a probability distribution. You can think of it as a complete map of the situation. It could be a table, a chart, or even a formula, but its job is always the same, to tell us the exact probability for every single numerical value our random variable can take.
Let's build a simple blueprint right now. Imagine a supervisor needs to pick 2 workers from a group of 3 men and 3 women. Our random variable, y, is the number of women chosen. If you work through all the possible pairs you could pick, you can calculate the exact probabilities. And as this table shows, there's a 20% chance of picking 0 women, a big 60% chance of picking 1, and another 20% chance of picking 2.
And seeing it as a bar chart, well, it just brings that blueprint to life, doesn't it? You can see the probabilities instantly. That big peak at y equals 1 tells you without a doubt that selecting 1 woman is by far the most likely outcome. This visual just makes those abstract numbers feel real, tangible.
Now, for any probability blueprint to be valid, it has to follow 2 golden rules. First, every individual probability has to be between 0 and 1, which makes sense, right? It's between a 0% and 100% chance. And second, when you add up the probabilities for all the possible outcomes, they have to sum up to exactly 1. This just means our blueprint has to account for every single possibility.
All right, now we're armed with our translator, the random variable, and our blueprint, the probability distribution. We can finally go back and solve that investor's dilemma. It's time to quantify the risk.
Let's walk through the solution. First, we define our random variable, y, as the number of high-risk assets we pick. Now think about it. Since there are only 2 low-risk assets available, we have to pick at least 1 high-risk one to get to 3 total. So y can be 1, 2, or 3. Next, we figure out the total number of unique 3-asset portfolios we can possibly create from the 6 available assets. The math tells us there are exactly 20 combinations. This number is the foundation for everything that comes next.
Okay, now we build our probability blueprint. For the first case, picking exactly 1 high-risk asset, there are 4 ways to pick that 1 asset and only 1 way to grab the 2 required low-risk assets. So 4 times 1 gives us 4 successful combinations out of 20 total, for a probability of 20%. For the second case, 2 high-risk assets, there are 6 ways to choose them and 2 ways to choose the 1 remaining low-risk asset. 6 times 2 is 12 combinations, which gives us a 60% probability. Finally, for 3 high-risk assets, there are 4 ways to do that, and that's 4 out of 20 or another 20%. Our blueprint is complete.
And there is our answer. The single most likely outcome for this portfolio manager is drawing a portfolio with exactly 2 high-risk assets, with a probability of 60%. We've officially moved from just a vague sense of danger to a precise, actionable number.
So why does this matter? Because this isn't just some neat math trick. This way of thinking is a fundamental building block for modern finance, risk management, and economic modeling. It's everywhere. So, what you should really take away from this is its immense practical power. Banks use it to model the number of loan defaults they might face. Lenders use it to create credit scores, and traders use it to price complex financial instruments. This is the math that helps power decisions across the entire economy. So, we'll leave you with this question. This whole framework gives us a powerful way to think about uncertainty. The next time you face a choice with random outcomes, whether it's in a game, an investment, or even just a daily decision, ask yourself, could I define a random variable here and build a probability blueprint to truly understand the odds I'm up against?